Welcome back. In part one of our deep dive, we walked through all the prep work that goes into getting a patient ready for the operating room. Well, today, in part two, we're prying open the lid on the anesthesiologist's toolbox to really understand the incredible drugs that make modern surgery possible in the first place.
You know, we all use that phrase, going under, and you might picture it as just falling asleep. But the reality, it is so much more complex and honestly, way more fascinating. It's not a gentle drift into dreamland. It's a profound, medically induced state that's being managed literally second by second.
Yeah, let's get one thing straight. General anesthesia is not sleep. It's actually closer to a carefully controlled, totally reversible, drug-induced coma. And to create this state, anesthesiologists have to become masters of pharmacology, solving what are basically the three fundamental problems of surgery.
Okay, so let's break these down, starting with the big one, consciousness. How do you safely and reliably turn off the human brain, and then keep it that way for the entire time a surgeon is working?
This, of course, is where sedative medications come in. But, and this is a huge but, they are absolutely not a one-size-fits-all kind of deal. The choice of which drug to use is governed by two really key pharmacological principles that every anesthesiologist has to have down cold.
What's so interesting here is how these two ideas, potency and efficacy, guide the whole process. So efficacy is about the maximum effect a drug can have. Can it get the job done? Potency is about how much drug you need to get that effect. A lot of drugs have the same efficacy. They can all get you to that state of unconsciousness, but their potency, and more importantly, their side effects, are wildly different.
And this table just lays it all out. This is where the real art of anesthesiology comes into play. Look at propofol. It's a total workhorse, used all the time. But see how it drops blood pressure? That makes it a terrible choice for, say, a trauma patient who's already bleeding and in shock. For that patient, you might reach for ketamine, which actually boosts the cardiovascular system. Or what about a patient with really severe heart disease? Well, for them, the incredible stability of etominidate might be the perfect fit. You see, the drug is always tailored to the patient's unique physiology. So once that initial IV drug has done its job and the patient is unconscious, that state is usually maintained for the rest of the surgery with an inhalational anesthetic. These are gases like sevoflurane that the patient breathes in through a breathing tube, and they keep the brain in that precise, controlled state for hours if needed.
So the patient is unconscious. Problem number one, solved. But that's only part of the story. What about movement? Because even the tiniest, most subtle unconscious muscle reflex could be an absolute disaster during a delicate brain or eye surgery. Let's see how they handle that.
To get that absolute stillness, anesthesiologists use a class of drugs called neuromuscular blockers, or paralytics. The best way to think about it is like this. The brain might send a signal down the spinal cord, telling a muscle to move. But these drugs act like a temporary off switch right at the very end of the line. They stop that signal from ever crossing the final gap to the muscle itself. It's like the controller's been completely disconnected from the game console.
Now, there are two main ways to flip that switch. The first, using a drug called succinylcholine, is like putting a key in the lock that turns it on for just a split second, but then breaks off, jamming the mechanism. You get this brief little muscle twitch, and then paralysis. The second method, using drugs like rocuronium, is a lot simpler. It's just like putting the wrong key in the lock. It just sits there, physically blocking the right key from ever getting in.
And knowing the difference between those two mechanisms, it's not just academic. It can literally be a matter of life and death. In patients with, say, severe burns or major spinal cord injuries, their muscle cells do something really dangerous. They grow extra, super sensitive receptors all over their surface. If you give those patients succinylcholine, the key that turns everything on for a second, all those extra receptors fire at once, releasing a massive, fatal surge of potassium into the bloodstream that can stop the hard cold.
This is just a perfect example of why every single anesthetic has to be so carefully personalized. A burn patient has so many extra receptors that they actually become resistant to the standard blocking drugs. But then you have the opposite situation. A patient with a condition like myasthenia gravis has far fewer receptors to begin with, which makes them incredibly sensitive. A tiny dose that would be totally fine for most people could cause a deep, prolonged paralysis in them.
We've seen these powerful, life-saving drugs that create the perfect conditions for surgery. But what happens when those very same drugs trigger a rare, 1 in a million genetic catastrophe deep inside a patient's own cells?
This is a condition called malignant hyperthermia, or MH. In people who are susceptible, they have a faulty gene that causes a tiny calcium channel in their muscle cells to get stuck wide open when it's exposed to certain anesthetics. And that floods the muscle cell with this uncontrolled, catastrophic torrent of calcium.
And trust me, this isn't a slow burn, it's an explosive chain reaction. The calcium flood makes muscles contract and become rigid, driving this insane metabolic frenzy. The body's oxygen use skyrockets, and it starts churning out enormous amounts of carbon dioxide and heat. In fact, a lot of the time, the very first sign is a rapidly climbing CO2 level on the monitor that just can't be controlled. That's the alarm bell telling the anesthesiologist that a crisis has just begun.
The response has to be immediate and perfectly coordinated. The second MH is suspected, all those triggering anesthetic gases get shut off. The team calls for help and for the dedicated MH emergency cart, while one person hyperventilates the patient with pure oxygen to flush everything out. The entire operating room team has a specific role in this highly choreographed emergency drill, and it all leads to getting the antidote in.
And this number, 36, this really drives home the challenge. That's how many standard vials of the antidote, dantrolene, have to be painstakingly mixed with sterile water and administered to treat just one 70-kilogram adult during an MH crisis. It is a true all-hands-on-deck effort.
Dantrolene is a true antidote. It's an incredible, life-saving drug that doesn't just treat the symptoms. It travels to the muscle cell and directly targets the molecular failure. It binds to and blocks that faulty calcium channel, stopping the whole catastrophic cascade right at its source.
So, we've journeyed through the absolute core pharmacology of general anesthesia. We've gone from inducing unconsciousness to ensuring total stillness, and even preparing for one of the rarest and most dangerous emergencies in medicine.
When you boil it all down, every single anesthetic is a dynamic balance of incredibly powerful drugs, meticulously tailored to one specific person. It's a controlled state, designed to protect the patient through the immense stress of surgery. But this brings up one last, really critical question.
I mean, really think about it for a second. After we've used these drugs to turn off all these systems to put someone into this profound state, how do we safely and predictably bring them back? How do you get them to wake up, breathe on their own, and protect their own airway again?
Well, that's exactly what we're going to explore in Part 3. Join us for the final part of this explainer, where we will dive into the science of waking up, the new reversal drugs that can undo paralysis in minutes, and the incredible regional techniques that can make one part of the body numb for surgery while the patient stays completely awake. We'll see you then.